Sequences. A sequence is a function such that the domain is positive integers. The notation is usually represented by a sub n, b sub n, etc. For example, if I have this sequence, a sub n equals negative 1 to the n squared, divided by quantity n plus 1. The lower bound, or the starting point, is at n equals 1, and this goes to infinity. So when n is 1, if I plug 1 in for n, I have negative 1 to the first, 1 squared, divided by 1 plus 1, which is equal to negative a half. When n is 2, negative 1 squared, 2 squared, divided by 2 plus 1. Or 4/3. When n is 3, negative 1 cubed, 3 squared, divided by 3 plus 1. Or negative 9/4. When n is 4, 16/5, and that pattern continues. So the alternating sign is some negative 1 to some power n. A recursive sequence is a sequence that defines terms as a function of previous terms. So if I make a few columns, 1 for the nth term, I'm going to list some terms, and then the recursive definition. So nth term, an equals 2n minus 1 plus 3. If I simplify this, I get 2n plus 1. When n is 1, first term is 3. When n is 2, next term is 5. Then the next term is 7, 9, and that pattern continues. To go from one term to the other term, I have to add 2 to the previous term. So this is called an arithmetic sequence. So there's a common difference. The difference is 2. The recursive definition, a1 is 3, and a sub n plus 1 is equal to an plus 2. The n plus first term is a sub n, or the previous term, plus 2. If I have the explicit form, a sub n equals 2/5 to the n. When n is 1, the first term is 2/5. When n is 2, 4/25. When n is 3, 8 1/25. To go from 2/5 to 4/25, I have to multiply by 2/5. to go from 4/25 to 8/125, I have to multiply by 2/5. Since there's a common ratio that I multiply by, this is called a geometric sequence. The recursive definition would be A1 is 2/5, since that's the starting point. The n plus first term, or a sub n plus 1, is equal to 2/5 times a sub n. Definition. Limit of a sequence. Let L be a real number. The limit of a sequence a sub n is written as the limit as n approaches infinity of a sub n is equal to L. A sequence converges to L if L is a real number. Otherwise, it is said to diverge. Theorem. Properties of sequences. If a sub n and b sub n are convergent sequences, and c is a constant. The limit as n approaches infinity of the sum or difference of two sequences. So limit as n approaches infinity of a sub n plus or minus b sub n is equal to the limit as n approaches infinity of a sub n plus or minus the limit as n approaches infinity of b sub n. the limit as n approaches infinity of c times a sub n is equal to c times the limit as n approaches infinity of a sub n. The limit of the product of two sequences. So the limit as n approaches infinity of a sub n multiplied by b sub n is equal to the limit as n approaches infinity of a sub n times the limit as n approaches infinity of b sub n. The limit as n approaches infinity of the quotient of two sequences, a sub n divided by b sub n, is equal to the limit as n approaches infinity of a sub n divided by the limit as n approaches infinity of b sub n, provided that the limit as n approaches infinity of b sub n is non-zero. The limit as n approaches infinity of a sub n raised to some power p is equal to the limit as n approaches infinity of a sub n raised to the p if p is positive and a sub n is non-negative. Theorem. If the limit as n approaches infinity of absolute value of a sub n is equal to 0, then the limit as n approaches infinity of a sub n is equal to 0. So for the following, determine if the sequence converges or diverges. A sub n is equal to the natural log of n divided by 3n squared. So the limit as n approaches infinity of a sub n, or natural log of n divided by 3n squared. If I take a limit, I have infinity in the numerator and infinity in the denominator, which is an indeterminate form. So I can use L'Hopital's rule. So this is equal to the limit as n approaches infinity of 1 over n divided by 6n. If I simplify this, limit as n approaches infinity of 1 over 6n squared. This limit is equal to 0, which implies that the sequence a sub n converges, since the limit is a real number. A sub n is equal to n divided by the square root of n squared plus 4. So the limit as n approaches infinity of n divided by the root of n squared plus 4. Infinity over infinity, which is another indeterminate form. I'm going to use a Calc 1 technique to simplify this. I'm going to divide by the highest degree term in the denominator. So n over the square root I'm dividing each term inside the root by an n squared, and outside the root is an n. And I still have to take the limit as n approaches infinity. So this turns into the limit as n approaches infinity of 1 divided by 1 plus 4 over n squared. So this limit is equal to 1 divided by the square root of 1 plus 0, which is 1, which implies that the sequence a sub n converges. A sub n equals n sine of 1 over n. If I take a limit as n approaches infinity of a sub n, this is equal to infinity times 0, which is an indeterminate form. So I'm going to turn this into a complex fraction. So limit as n approaches infinity of sine of 1 over n divided by 1 over n. Now if I take a limit, the numerator is 0, the denominator is 0, which is still an indeterminate form, but I can use L'Hopital's rule. So this limit is equal to, if I differentiate the numerator, cosine of 1 over n multiplied by negative 1 over n squared from chain rule. Derivative of the bottom is negative 1 over n squared. So I have a common factor in the numerator and in the denominator. So this limit turns into the limit as n approaches infinity of cosine of 1 over n, which is equal to cosine of 0 or 1, which implies that the sequence a sub n converges. A sub n equals n plus 1 factorial divided by n factorial. If I take a limit as n approaches infinity of a sub n plus 1 factorial divided by n factorial. Infinity divided by infinity, which is indeterminate. But I can't take derivatives of factorials. So instead, I'm going to expand out the top factorial. So this is equal to the limit as n approaches infinity of n plus 1 times n minus 1 times n minus 2 and so on. I'll leave it as an n factorial. Denominator is an n factorial. Now I have a common factor of n factorial on top and n factorial on the bottom. So this is equal to the limit as n approaches infinity of n plus 1, which is infinity, which implies that the sequence diverges. A sub n equals negative 3 to the n. So the limit as n approaches infinity of negative 3 to the n, this diverges since this is all over the map. Theorem. If an equals r to the n, is convergent if negative 1 is less than r, which is less than or equal to 1, and divergent otherwise. The limit as n approaches infinity of r to the n is equal to 0 if negative 1 is less than r and is less than 1, or 1 if r is equal to 1. So determine if this sequence is convergent or divergent. A sub n equals negative 1 to the n. Limit as n approaches infinity of negative 1 to the n is divergent. A sub n equals 1/3 to the n. So the limit as n approaches infinity of a sub n is equal to 0 based on the theorem, which means that this sequence is convergent. If a sub n equals 1 plus 5 over n to the nth power, so the limit as n approaches infinity of 1 plus 5 over n to the n is 1 to the infinity power, which is an indeterminate form, since inside the parentheses is approaching 1. So I'm going to let y equal this limit. The limit as n approaches infinity of 1 plus 5 over n to the nth power. Then I'm going to take a natural log of both sides. So I'll natural log both sides. Then there's a property that allows me to interchange the natural log and the limit. So this is equal to the limit as n approaches infinity of the natural log of 1 plus 5 over n to the nth power. Then, with the rules of logs, I can bring this exponent to the front. So this is equal to the limit as n approaches infinity of n times natural log of 1 plus 5 over n. If I take a limit on the right side, I have infinity times 0, which is still an indeterminate form. So I'm going to rewrite this as a fraction. This is equal to the limit as n approaches infinity of the natural log of 1 plus 5 over n divided by 1 over n. So now if I take a limit, 0 over 0, which is an indeterminate form, but I'm able to use L'Hopital's rule. So this is equal to the limit as n approaches infinity. The derivative of the numerator is 1 over 1 plus 5 over n times the derivative of the inner function, negative 5 n to the negative 2, divided by the derivative of the denominator is negative n to the negative 2 power. I can cancel the negatives, and I can cancel the n to the negative 2 power. So I'm left with the limit as n approaches infinity of 5 divided by 1 plus 5 over n. This limit is equal to 5, but if I go back to the beginning, y was my original limit, and the left side is the natural log of y. So the natural log of y is 5, which means y equals e to the 5th power. And y is this original limit, which is the limit of the sequence. Since that's a real number, this implies that a sub n, or the sequence a sub n, converges, or a sub n is convergent. A sub n equals sine of n divided by n. So sine is bounded between -1 and 1. So -1 is less than or equal to sine of n, which is less than or equal to 1. If I divide the left side, the right side, and the middle by n, -1 over n is less than or equal to sine n divided by n, which is less than or equal to 1 over n. Now if I take a limit, the limit as n approaches infinity of -1 over n is less than or equal to the limit as n approaches infinity of sine of n divided by n, which is less than or equal to the limit as n approaches infinity of 1 over n. The left side, that limit is 0. The right side, that limit is 0 also, which implies that the limit as n approaches infinity of sine n over n is equal to 0 as well by squeeze theorem. Or sandwich theorem, which means that the sequence a sub n converges. Definition: a sequence is increasing if a sub n is strictly less than a sub n plus 1 for all n. A sequence is decreasing if a sub n is greater than a sub n plus 1 for all n. Definition of monotonicity or monotonic: a sequence is monotonic if the terms are either non-decreasing or non-increasing. So non-decreasing means A1 is less than or equal to A2, which is less than or equal to A3, and so on. AN plus 1. Non-increasing A1 is greater than or equal to A2, which is greater than or equal to A3, which is greater than or equal to AN, which is greater than or equal to A sub n plus 1, and so on. Bounded above. If there is a real number m such that A sub n is less than or equal to m for all n, then m is an upper bound. So the sequence does not go beyond m. Bounded below. If there is a real number n such that A sub n is greater than or equal to n for all n, then n is a lower bound. A sequence with both an upper bound and a lower bound is bounded. A sequence with both upper and lower bounds is bounded. If a sequence theorem. If a sequence A sub n is bounded and monotonic, then it converges. Prove that the sequence is increasing. Prove that the sequence a sub n is 2n minus 3 divided by 3n plus 4 where n goes from 1 to infinity is increasing. One way to prove that this is increasing is I'm going to define this to be some function f of x. So f of x is 2x minus 3 divided by 3x plus 4. In Calc 1, to prove that something is increasing, we took a first derivative. So f prime of x, I'll use quotient rule. 3x plus 4 times 2 minus 2x minus 3 times 3 divided by 3x plus 4 quantity squared. If I simplify this, this is equal to 17 divided by 3x plus 4 squared. So this is always positive for all x. Provided that x cannot equal negative 4/3. So the first derivative is always positive. Therefore, the sequence a sub n is increasing for all n greater than or equal to 1. So this sequence is increasing, and also if I take a limit as n approaches infinity, it's equal to 2/3.